Welcome to section 1.7, day 2, inverse functions and their applications. Today we're going to use function composition to show functions are inverse functions, and then we're going to apply inverse functions to real-world problems. So key concept, two functions f and g are inverse functions if and only if, when you take the composition f of g of x, you get x back, the identity function comes back. When you take g of f of x, you also get the identity function x back. That's what we have to do today. If it says to show it, you're going to show that the compositions both go to x, and that proves that we have inverses. So first thing it says is show f of x equals 18 minus 3 of x, and g of x equals 6 minus x over 3 are inverses. So f of g of x. I think this notation is a little easier to use than the f with the circle between. Use whichever one you want, but I think this makes it more easy to understand what we're doing because we're plugging the g function into the f function. We have 18 minus 3, and the g function is 6 minus x over 3. And then we distribute. We have negative 3 times 6, negative 18. Negative 3 times negative x over 3. The 3's cancel out, the negatives cancel out, and we get plus x. And this is x. Then we'll do the g of f of x. Now we're plugging in 6 minus, for x we have 18 minus 3x. This is over 3. We have 6. We can break, since the numerator has a plus and a minus, we can actually break this into two things, or we can just cancel out a 3 of every term. As long as we can take it out of every term, we can do this. Now remember, this is a minus, and we're minusing this fraction. So 6 minus 6, the negative goes to the negative x. So we get negative 6 plus x, or minus 6 plus x, and we get x. And then we stay at the end as we say, since f of g of x equals g of f of x, and they both go to x, then f of x and g of x are inverses. So we want to say this, if it says to show it, first show that both go to x, the identity function, both compositions, and then state this, since f of g of x equals g of f of x equals x, then f of x and g of x are inverses. This is showing it algebraically. It's sort of like an algebraic proof. It's what we are doing. So then we have show f of x is 6 over x minus 4, and g of x 6 over x plus 4 are inverses. Again, we're going to do our compositions. So we're going to plug the g into the f function. We have 6 over x plus 4 minus 4. From here we simplify things out. Simplify. We have 6 over 6x because the negative 4 and 4 cancel out. To get rid of this division by a fraction, we multiply by the reciprocal. You can do it two different ways. Sometimes you can show it like this. I'm going to multiply by x over 6. These all cancel out in the denominator. This is 6 over 1, so these cancel out, and we get x. We do the same thing now. We do g of f of x. And we start getting some of these compound fractions we got to work with. So now we're going to take 6. The x is 6 over x minus 4. And then we have plus 4 on the outside. And again, we have these compound fractions. We're dividing by a fraction, which is multiplying by its reciprocal. And if it helps you look at it this way, this is what I usually do. These cancel out to 1. This is, like I said, over 1. The 6's cancel out, and we're left with x minus 4 plus 4. And when you do this, you get x. And again, we have our statement. Since f of g of x equals g of f of x equals x, therefore f of x and g of x are inverses. If you do not get that back, if you don't get the identity function back in either of them, they are not inverses. Here's another one we're going to do. We have f of x equals x squared plus 10, and we have g of x equals square root of x minus 10. And again, we do our composition. Part of why we're doing these is that you guys get to see different algebra skills you may have not used for a while. So we have square root of x minus 10, put in for x. This is all squared, plus 10. This becomes x minus 10 plus 10. And this is x. We do the other composition. Now we're going to plug the f function into the g function. So we have square root of x squared plus 10 minus 10. This is the square root of x squared, which is x. And we have our, again, we showed that they both equal identity function and our statement. Since f of g of x equals g of f of x, and they both go to x, therefore f of x and g of x are inverses. So that's our first part of our lesson today. Finding the compositions, get the identity function back to show that we have inverse functions. If we don't get the identity function back, either you did something wrong or we do not have an inverse. All right, next thing, manufacturing. We're going to do some real world problems here. The fixed cost for manufacturing one type of stereo system is $96,000 with a variable cost of $80 per unit. The total cost, f of x, of making x stereos is given by the function f of x equals 96,000 plus 80x. So explain why the inverse function exists and then find the f inverse. Well, we have an inverse because this is a function and it passes a horizontal line test. It's an easy way to look at it. So it passes the vertical line, it's a function, and it passes a horizontal line test. And that's what I'm going to say. Passes vertical line and horizontal line test. And if you think about this, we can't, if we're making so many stereos, we can't change the cost. Each stereo is 80 bucks. So one stereo can't have two different costs to it associated with it. We want to do the inverse, so we change our f of x to y, and we have 96,000 plus 80x. Interchange our variables. Solve for y. So I'm going to subtract 96,000 for both sides. And then divide by 80. When I divide by 80, I'm going to rewrite this to put the y over on the left. And we have x minus 96,000 over 80. All right, this is my inverse. So f inverse of x is x minus 96,000 over 80. Next part, it says, what do f inverse and x represent? Remember, f inverse of x was x minus 96,000 over 80. Well, if in the original function we had stereos was x and cost was the f of x, it's changed. It's just the opposite. So now x is the cost, and f of x is stereos, or f inverse of x is stereos. We change our x and a y around. And then it says what restrictions, if any, should be placed on the domain of f of x. Well, the f of x domain, think about this logically, we're making stereos. We can't make less than 0 stereos. We have to make 0 or greater. We can't have negative stereos. So our domain has to be at least from 0, no negatives. For f inverse of x, since we're talking about cost, for f inverse function, think about this. Originally, we said that it was $96,000 with our fixed cost and our number of stereos, so we always had a cost of at least $96,000. So in our inverse function, our domain has to start where our total cost was originally, because it's going to cost us $96,000 no matter how many we make. This goes to infinity. And again, if you think about it, we are interchanging the x and the y's around again when we do the inverse. Originally our range started at 96,000, and our domain starts at 96,000. The last part says, so the final thing we're going to do is we're going to use our inverse function and find out how many stereos are made if our total cost was $216,000. So we are going to plug in 216,000 for X. We're going to evaluate our inverse function, which will tell us how many stereos were built. So what we're doing is plugging it in. And when you do this, you get 120,000 over 80, which when you do this on a calculator is 1,500 stereos. So if $216,000 is spent, that means that 1,500 stereos should have been produced. This is actually something that businesses do to see how things are going. They can see what their production costs are. They should have a good idea how many should be produced, and they actually compare it to what they actually produced. And they'll tell if they have inefficiencies going on or something's going wrong with the production line. That is all for section 1.7 day 2. Today we did inverses with their composition of functions to make sure we get the identity back. So we showed if we had inverse functions, and then we showed a real world application. Thank you for watching and have a nice day.